So in electrostatics, we learned Coulomb's law and all. And right now, today's focus is on capacitance and electric potential. We already know. So there are some standard results which you people are already aware. I'll quickly brush them. I remember, and I'm sure all of you have learned electrostatics. You have learned Coulomb's law for a point charge. Q1, Q2 upon R square, where 2 point charges, they exert a force of uh, electric force. They will exert on each other will be equal to 1 upon 4 pi epsilon naught Q1, Q2 by R square, where R is the distance between them. And if they are kept in space, this is the relationship. If there is a medium having dielectric constant K, then you will have 1 upon 4 pi epsilon naught K here in the denominator. And this is the Coulomb's law. It has a direction and cap. I'll say if both the charges are positive, they repel each other, they will exert a force of repulsion on each other. If they are negative, still they will repel. And if they are, one is positive, one is negative, they will attract each other. Now, coming to the quick brush up of the key formulae. Then you learned a principle of superimposition that if there are many charges and you want to find the net force on a charge Q naught. So if there are many charges, say Q1, Q2, Q3, Qn. So all you have to do is independent of the presence of others, you just find out the net force due to one charge, find the net force due to the other charge, find the net force due to the third charge, and so on. And then you do the vector sum, you'll get the net force. This is called principle of superimposition. The same thing holds true for electric fields also. Then we studied electric lines of force. There are two important results that I would like to mention to you here. One is E dot dl, line integral of electric field. What does it represent? Suppose there is a electric field in a region and you are at point A and you do, this is point A and this is point B. And if you find the line integral of electric field from A to B through any path, A to B, what does this represent? This represents VA minus VB. Most of the times, this is the potential difference between A and B. So just try to understand. If there is no electric field, the potential of A will be same as potential of B. There will be no potential gradient. If there is an electric field, there will be potential difference between A and B. One will be at a higher potential, one will be at a lower potential. And sometimes some people do get confused with this, that in most of the books, they write minus E dot dl. So that is nothing else. It is the same thing. When you say VB minus VA, final points potential minus initial points potential will be equal to minus E dot dl, line integral of electric field from A to B. I am assuming in electrostatics chapter, you have done this. So whichever way you remember this equation, you should know line integral of electric field from one point to another. If you go to a general position, here you choose a small element dl and you do E dot dl. E may be in any direction. So E dot dl from here to here will give you the potential difference between A and B, and we'll be using this result in capacitors. That's why it's important for me to highlight this. There was another thing, E dot ds, surface integral of electric field, which was for any surface, this gives you the flux passing through that surface. And we also learned Gauss theorem that if there is a closed Gaussian surface, in that case, E dot ds for that closed Gaussian surface is equal to Q enclosed upon epsilon naught. This was Gauss theorem and this was general flux, Gauss's theorem. I'm sorry. This is Gauss theorem. Now, I'm quickly brushing up because these results. Now, then you learned that for a point charge, for a line distribution of charge, if there is an infinitely long line having a charge per unit length lambda, And you want to find the electric field at a distance r from it, which is perpendicular, r, perpendicular distances are. Now, what was the result? We used Gauss theorem and we found the result that electric field here, E lines, will be all perpendicular to the radially outwards from the wire, and electric field direction will be in this direction, and the magnitude here was lambda upon 2 pi epsilon naught r. And direction is specified as I'm showing here. This is the direction at this point. And we found this result using Gauss theorem. If you recall, we considered a Gaussian surface of radius r, and then we found the flux through the surface and equated the flux to charge enclosed upon epsilon naught. And this was the result, lambda upon. You have to remember this result, that for a line distribution of charge, electric field can be found using this. Similarly, we had a sheet, thin conducting sheet, one layer of charge, which is like a thin non-conducting sheet, and it had charge per unit area as sigma, and we found the electric field intensity at a point d distance away from the sheet, infinite conducting sheet, was how much? Sigma upon 2 epsilon naught. We found this. We can use Gauss theorem also and find it quickly. I can quickly show you, but right now I'm wanting to focus on the chapter called capacitance. So I'm just reminding you these results, but very quickly I can say you make a Gaussian surface. Oh my God. Which is d distance here and d distance this side, and you can see E lines will be perpendicular to the electric field lines will be perpendicular to the infinite conducting plate, and therefore E dot ds for this side, if I take E and surface area will be in this direction perpendicular to the surface, E dot ds for the curved surface will be 0. E dot ds will be only for the lid, and E into A plus, similarly for this side you will have EA, you will have EA here, E into A plus E into A, 2 EA will be equal to charge enclosed sigma upon epsilon naught, sorry. Now, this is sigma into A. This is charge enclosed upon epsilon naught. Flux is equal to charge enclosed upon epsilon naught as per Gauss theorem, and the result comes E is equal to sigma upon 2 pi epsilon naught. This is for, please remember, thin, non-conducting, infinite plane. If I have a conducting sheet, it will have sigma on both sides. And for that, the result will come out to be sigma upon epsilon naught, the electric field. And you can see the electric field intensity doesn't depend on the distance for an infinite conducting sheet. So for all points close to a plate whose dimensions are large, I can assume that the electric field will be independent of the distance from the plate. So this is an important result. And again, we used Gauss theorem in deriving this result. And I'm quickly now, we also did dipole. You have a charge Q, a charge minus Q placed at a small distance from each other, and say that distance is d. And then this is called a dipole. You can find the electric field intensity at any point on this line is called equator. This line is called this is called the axis, and this is called equator. Now, if I want to find electric field at any point on the equator, I can find the electric field due to this point charge. This will be in this direction. I can find the electric field due to this point charge in this direction. I will resolve them. I'll find out this components of both will get added. These two components will get cancelled. They are equal and opposite. Now, and you will get a result. And for equator, we can find out the net electric field also. Potential on every point here will be 0. Why will potential be 0? Because KQ by R, that will be like 0 here. For equator, every point, and electric field will come out to be in this direction, net. And we have those results also with us. And for dipole, we have the torque acting on a dipole placed in an electric field is P cross E. This is the torque. You have to remember these results. I'm quickly brushing up your electrostatics key things so that in capacitors, when we use all these key things, we are able to remember that. Now, and then you had the potential energy of a dipole placed in an electric field can be written as minus P dot E. These two results you should remember. There is one more result I want you to remember is if this electrostatics chapter is same as gravitation. The only difference is charges are of two different kinds. One is positive, one is negative. Masses only attract, they don't repel each other. Charges have attraction and repulsion. That's the only difference. Otherwise, electrostatics, mostly the things are in parallel in gravitational force. And similarly, so all these results that you're learning, for example, there is a shell, there is a spherical shell. This is an important result asked a lot of many times in comparative exams. If there is a hollow spherical shell made up of a conductor, so if I want to find it has a uniform charge spread across its area. So first of all, understand this. If there is any metal, the electric field inside, if suppose this is a conducting, let me see, this is a metallic sphere. Understand this, metallic sphere, and it is solid. This is an important result. You all need to understand this. Now we are about to transition into capacitance. So please be patient, attentive. This is an important result. If Q charge is given to a metallic sphere, which is solid, there is metal everywhere. Everywhere there is metal. It's not hollow. It's not a shell. So whenever you will give a charge, if there is symmetry, then obviously it will be uniformly distributed. If it is a spherical shell, conducting shell, and it is solid, so the whole charge will come to the outer surface. There will be no charge inside. Why? Can anyone explain to me? I will give you the logical explanation right now, assuming that all of you are aware. Because inside a metal, inside the solid metal, there are free electrons which are free to move. The moment there is a net electric field here inside, if suppose by any chance there is a net electric field, those charges will start moving in. If they are positive charges, they will move in the direction of electric field. If they are negative charges, they'll move opposite to if there is an electric field inside. Now, so they will keep moving till the whole charge comes to the outer surface and inside electric field is 0 and they will repel each other. Suppose I give Q plus charge, all the small positive charges, they will repel each other and try to go for maximum separation. They will come to the outermost surface. Inside, electric field has to be 0 inside a metal, and free charge, Q free is also 0. These two are very important things. Please understand this. Now, let me generalize. If there is any conductor which is solid conductor, please pay attention. Very important to understand electrostatics as well as the whole capacitance and everything. Now, and if it is a solid conductor, inside a solid conductor, always electric field has to be 0. Free charge, you give it any charge, keep it anywhere, it will come to the outer surface and Q free inside is 0. The whole charge comes to the outermost surface. It may be uniformly distributed or non-uniformly distributed, but it will be on the outermost surface. There will be no free charge inside the solid conductor. This is one very important result every child should understand. Now coming to a spherical shell. Now, if it is given a charge Q, and its radius is say r, and I ask you, how do you find the electric field or potential at a point P1, which is outside the shell? How do you find? So there are three regions. One is outside the shell. So this is one point which is outside the shell. It can be anywhere from R to infinity. There is a second point which is on the surface. There is a third point which is inside it. Suppose this is x1, this is x, this is r, obviously radius, and this is x2. Now, P1, P2, P3. What is the difference? P1 point is outside the shell. Please remember this result, very, very important. P2 is a point on the surface of the shell, and P3 is a point inside the shell. Inside. Now, we will, and Q charge is given to this spherical conducting hollow shell. This is a hollow conducting, or for that matter, it can be non-conducting also. Non-conducting. The only difference is, if it is non-conducting, we cannot guarantee that the charge will automatically get uniformly distributed. If it is conducting, I give it a charge Q, it will uniformly get distributed. If it is non-conducting, then we have to uniformly distribute the charge ourselves. It will automatically not get, because non-conductors do not have free electrons which will carry the charge and do the charge distribution. So, but if anyhow we are able to achieve that there is a uniform distribution of this Q charge on the outermost surface, so we know uniform Q is, लिख लीजिए, uniformly distributed. Uniformly distributed. So whether it is conducting or non-conducting, in both the cases, the results will remain same. The Q has to be uniformly distributed over the surface. That's the condition. Now, for all the points outside, you will assume that the whole charge of the shell is at the center and treat it as a point mass, a point charge. So if I want to find electric field at this point, this will be 1 upon 4 pi epsilon naught. Electric field at point 1 will be 1 upon 4 pi epsilon naught Q upon x1 square. I assume this whole charge to be at the center, treated as a point charge, and found the electric field. And same way, you can find the potential also here. So these results come after integration. They come using Gauss theorem. Whatever way we arrived at these results, I want you people to remember these results for sure. Oh yeah, this pen is again going to cause problem. In between, I'll give you questions and then, okay. Now, E2, sorry, for surface points also, the results remain the same. So for outside points or surface points, both, we will get the same result, and the result will be, you will treat the point charge to be at the center, and then find out the results, whether it is potential or electric field. For points inside, the electric field due to the shell charge will be 0. This is the final result you should remember, and potential inside will be same as that on the surface. Now these results must be on your tips. You should know they have been derived using calculus also. They have been derived using how can it reach 0? Now coming to, they have been, so these results are very important, and we will be using them in capacitance chapter. Now, so, now coming back, 1 second. Okay. Now, we will go to the next part. I am giving you some one sec. I'm just trying to sort out this marker thing, the problem of this. Okay. Now, so dear children, now when we are, so these results you will need, and we will be little careful, fast, थोड़ा सा समझ के चलेंगे. बीच में मैं अपना पेन भी चार्ज कर लूंगा when I give you something. Now, let's come to potential, electrostatic potential, which is an important part. And let's come to a capacitor now. What is a capacitor? Capacitor. Any device which is used to store charge. Dipole results, dear children, right now, because I very clearly specified that I want this lecture, every time this happens, so I end up going to the basics and I start doing the Coulomb's law and all. So what I'm wanting is to focus more on capacitors, KVL, Kirchhoff's voltage law, that should be applied, how to focus on capacitance and its equivalent capacitance and all those things. Key things I want to tell today. And I want to focus more on capacitor chapter. That's why I am avoiding going back to dipole or these shells results. I've quickly brushed up, told you all these results are given, the key formulae are given in your books, and you can see there that you will get, otherwise I can hold a special lecture on. In fact, I'm planning to do that, but today's lecture for a specific reason is focusing on capacitance, and let me do that. Let me first finish that, then we'll go back anywhere. Now, any device, any conductor or any device which is used to store charge. No, any device, any body which is used to store charge, if it is a conductor and I put charge on it, so it will store some charge. This is a capacitor. There is an isolated sphere and it has a radius r. I give it some charge q. Can anyone tell me how do I find its potential? And the capacitance of a body is defined as, give it an imaginary charge q and find its potential. Q by V, the ratio, is defined as the capacitance of that body. This is the basic definition of capacitance of a body. But please try to understand what is happening. If I give a charge Q to this sphere, what will be its potential? Its potential, it is a conducting sphere. I can assume the whole charge to be at the center. The potential will be 1 upon 4 pi epsilon naught Q upon R. This will be the potential. And capacitance of this will be Q divided by V, which will be C will be 4 pi epsilon naught R. And it is the capacitance of a isolated sphere, single sphere. So capacitor के लिए जो आप सीखते हैं कि there are two parallel plates, let's understand the logic behind it. If this is one plate, I have drawn it too thick. These are two thin plates placed close to each other. Suppose I have given, there was only one plate and I have given it a charge, say Q1. How will the charge, it's a metallic plate. How will this charge be distributed on this plate? Can anyone tell me? Quick. Q1 by 2 on this side and Q1 by 2 on this side, right? Inside the metal, electric field will be 0. Inside the metal, Q free charge will be 0. And it's a thin conducting sheet. All of you agree to this? Give me a thumbs up if you have understood this. This is the charge distribution for an electric plate. If I give it charge Q, it will be uniformly distributed on both sides. Q by 2, Q by 2. Good. I want little participation. Now, if I have, instead of this, I have two sheets which are placed close to each other. Two sheets which are placed close, thin conducting sheets which are placed close to each other. Now, if I have one sheet, which is this, I have another sheet, which is this, and I have given Q1 charge to this and Q2 charge to this. Now, please help me find out what will be the charge. Suppose the charge here is X, Y, Z, P. Find the values of X, Y, Z, P. Find the values of X, Y, Z, P. There are two thin plates which are having charge Q1 and Q2. And I have kept them near each other. Find the charge distribution on each plate. How do I find X, Y, Z, and P? Can anyone do it? Give it a try. I will solve it for you. Just find out. All of you give it a try. Let me see how will you do it. And this is the beginning of capacitance. You will start learning capacitance properly from here. And I will not make you cram results. You will just be remembering the standard definitions, and you will be able to solve most of the questions of full capacitance. Just pay attention and try to find out what will be the charge distribution be like. Give me your results. Tell me your results. I want to see. I'm going to YouTube also, and I'm trying to see if people are answering there. The question is, okay. The question is, find the charge distributions. How will each layer, what charge? This is Q1 charge given to this plate, Q2 charge given to this plate. Find what will be the charge distribution be like. Quickly tell me on each plate. It will be uniform, but how much will be the value out of Q1 and Q2? Just, okay, let me do it for you. So, first of all, understand this. Suppose this is Q1. So, if I assume the charge here is Y, so this will be X plus Y should be equal to Q1. This is what? Conservation of charge. Z plus P is equal to Q2. This is also conservation of charge. So now this problem becomes, if you were just applying this much information or knowledge, you could have said, this is Q1, this is Q2. If I assume this is X, this side will have Q1 minus X. And this side is Y. So this will have Q2 minus Y charge. This much we know. So the moment you introduce less variables, the easier it becomes to solve. You don't have too many equations then, need too many equations then. Now coming to, can I apply Gauss theorem here? in this region, can I apply Gauss theorem? And if you know Gauss theorem, here electric field inside the metal is zero. So the flux will be zero, E dot ds. Here electric field is zero, magnetic flux will be zero. Electric field lines, suppose it's a positive charge or a negative charge, whatever, E lines will be in this direction only or in this direction. They will be perpendicular to the plates. And we have seen this result that if a plate has a charge, the E lines are perpendicular to the plates. So E dot ds, electric field is in this direction. Electric field lines are in the electric field is in this direction, surface's area is in this direction. So for this surface, E dot ds. Similarly, for this surface, E dot ds will be, this is surface area, this is E direction. So net E dot ds for this full thing, for this closed Gaussian surface, which I will mark with, say, the red color. And this is like a closed Gaussian surface, cube, you can say. Now, for this, net flux is zero, should be equal to charge enclosed. Charge enclosed upon epsilon naught. So charge enclosed will come out to be x plus y. So x plus y should be zero. Therefore, x should be equal to minus y. Now, if you just put these two values to x should be equal to minus y. So if this is any charge, x, so now, one more thing. I will use one more equation to, there are two unknowns, x and y. I need one more equation. So one we used Gauss theorem, and second we will use, second we'll use net electric field inside any sheet, any point inside the sheet will be zero. How do you find that net electric field here is zero? There are four layers of charge. One is this, one is this, one is this, one is this. How do I find the net electric field here zero? There are four layers. One layer is this, divided by area will give me sigma, divided by area will give me sigma, divided by area, divided by area. All these will give you net electric field here is zero. We know due to one layer, it is sigma upon 2 epsilon naught. So the net electric field inside this point due to this layer, layer 1, layer 2, layer 3, and layer 4 will be how much? Due to layer 1, it will be sigma, which is Q1 minus X upon area, this upon 2 epsilon naught. And I am assuming this to be positive, so it will be in this direction. Now, X will be in this direction, X upon 2 epsilon naught A. Similarly, for Y, again, I'm assuming Y to be positive. It will be in this direction. Y upon 2 epsilon naught A. And Q2 minus Y upon 2 epsilon naught A. All the four layers will produce the net electric field at a point inside the metal plate will be, this point will be zero. We found the net electric field due to all the four layers of charge, equated it to zero, and this will, okay. What we are doing is, see this, if I have two plates, this is, I can give you a shortcut also. This is Q1, this is Q2. I gave them two charges. I wanted to find what is the charge on each side of the plates. I assume this to be X, so it will be Q1 minus X. I assume this to be Y, it will be Q2 minus Y. And I asked you find the value of each X and Y. Each plate will have, each surface will have what charge? That was the question. Now, when I'm trying to explain the solution, one thing I told you using Gauss theorem, we know X plus Y should be zero. That is X equal to minus Y. This result we got using Gauss theorem. Please note it down. And second, I'm saying I'll find the net electric field due to this layer, this layer, this layer, and this layer of charge. These are 4 layers of charge. And net electric field here will be 0 inside the metal. So I'm just going to put that. And from there, you will get Q1. You will divide this by area. Then you will say sigma by 2 epsilon naught. So I'm just quickly writing the result. Q1 minus X plus. So these two are equal and opposite. We have seen that their net electric field will be 0 anyways. Now this and this should equate. This should be equal to Q2 minus Y. From here, you will get, I can put X equal to minus Y. So Q1 minus Y is equal to Q2 minus Y. And this gives me X is equal to minus Y. This gives me Q1 minus Q2 is equal to minus 2Y. So Y is equal to Q2 minus Q1 upon 2. So this will be the result. Now, the summary of this result that I want to give you is, now this is Y. Similarly, you will get X. And if you will find the charge here, it will be coming out to be Q1 plus Q2 by 2. Charge here, Q1 plus Q2 by 2. And inside you will have X and Y. Now, you using this result, Y, using this result that we derived, we will get the value of X. It will be Q1 minus Q2 upon Y. And when you put the value of X here, you will get this result. You will put the value of Y here, you will get this result. Q1 plus Q2 by 2. Now, so just summarizing this result quickly, because here, if I give Q1 charge to this plate, Q2 charge, now this is for a capacitor that you need to understand Q2. You will find that the charge here comes out to be Q1 plus Q2 by 2, Q1 plus Q2 by 2 on the outermost surfaces, and inside charge is coming out to be, suppose this was X, so it comes out to be Q1 minus Q2 by 2, and this comes out to be minus of Q1 minus Q2 by 2. Now, these are the results. Now, try to understand this. What I'm saying is, K, these are the results. Now, when you treat them as, so please see this, if these two sheets, if I bring them in, connect with each other, what will happen? If I connect them with each other, this charge will disappear. If I just touch them together. So the whole charge Q1 and Q2 is coming out on the outer surfaces and there is no charge inside. But because I have not connected them, I have not touched them, and I have just brought them close to each other, there is some distance here. So there will be charge, and that charge will be this much. Now, when you are dealing with a parallel plate capacitor, children, I am giving you something which is really beautiful, interesting. सब लोग आपको वो एक डायग्राम बना देंगे और बोल देंगे कि ये पैरेलल प्लेट कैपेसिटर हो गया, और बहुत आसान होता है उसे करना, सीखना और उससे क्वेश्चंस होना, बट ये कॉन्सेप्चुअल क्लैरिटी के लिए बहुत जरूरी है. प्लीज पे अटेंशन. नाउ, if there are any two plates, why do we need to, for a parallel plate capacitor, why do we need another plate? What is happening? Suppose this is given charge Q. I could have said this plate can store charge, and I could have used this plate as a capacitor. But then we realize that when a plate is given a charge and another plate is brought close to each other, this will develop some, suppose this is a positive charge. This was distributed, it will develop some negative charge here and a positive charge here. And if you find the electric potential of this plate, you will have potential due to its own charge, potential due to this, and potential due to this. The net potential will decrease a little bit. So the capacitance is defined as Q by V. So if potential decreases, then the capacitance increases. So if you brought another metallic body near a body, the purpose is to decrease the potential of that body so that its capacitance increases, the capacity to store charge increases. Now, if I earth it, the other plate, that ensures that this charge flows down to the earth, and this negative charge will be producing a higher negative potential here. This will further decrease, therefore capacitance will increase. So why do we choose two parallel plate capacitors? This was the logic I was trying to give. If there is a plate, there is another plate, and I connect them to earth one plate, and I give a charge Q to one plate. Now, how will the distribution be like? This will have zero charge, this will have zero charge on outer surfaces. Please understand this, on outer surfaces. And inside surface, the whole charge will go inside, and this will be minus Q. Now, again, this is similar to that situation that the two plates brought in touch with each other. I earthed it, then the whole charge will flow to the ground. So outer surfaces have zero charge, and this inner charge will exist. And that inner charge, try to understand this. Here, whenever you have two plates placed close to each other, for outer surfaces, it's very easy to find the charges. You just assume them to be connected or brought very close so that they can be treated as a single thick plate, and seen from far, you will find outermost surfaces will have zero charge. So just to give you that clarity, I explained this to you. Now, coming back to, so this is the charge distribution, and this arrangement is called a parallel plate capacitor. Please understand, if you have any device, if you have a sphere, a metal, another metal capped, these two are called the plates. It doesn't matter. It doesn't necessarily have to be a plate. So for a capacitor, whichever is being used to store charge, the positive and the negative charge stored on two different bodies, each of them is called a plate. So they are still called plates of a capacitor. That's a convention. Second, in a capacitor, you saw there was plus charge and minus Q charge. In a parallel plate capacitor, you saw there was plus Q, there was minus Q. Net charge is zero. One is earthed. Net charge is zero, but still you say that charge on the capacitor is Q. So please understand, we are not talking about net charge. Net charge on the capacitor is zero, but the charge stored on a capacitor is defined as this. One of the plates, charge of one of the plates. Now coming to any capacitor is denoted by this symbol. A resistor is denoted by this symbol. A battery is denoted by this symbol. And all of you should know that in a battery, this is the positive terminal, this is the negative terminal. Suppose I say this battery is 20-volt battery. So if you are going while moving in a loop, you are going in this direction, you will say your potential was initially less and potential here is high. So your potential increased. Potential will increase. So you will write plus 20. Potential increase is being considered as plus, potential decrease will be considered as minus. So when you go in a battery from this side to this side, you write plus 20. If you go in a battery, I'm trying to tell you when we will be using Kirchhoff's voltage law for capacitors, how will we write the equation? So just please pay attention. Now, in the opposite direction, if I'm going in a circuit, in that case, I am going from a positive plate to a negative plate. So potential is decreasing. So I'll use minus 20 volt. This is for a battery. For a current, if suppose current is flowing in this direction, R is the resistance. Current always flows from higher potential to lower potential. So all of you can understand this has to be higher, this has to be lower. Current flows from higher to lower direction, higher potential to lower. Now, you can see if I am going in this direction in a circuit, I will be writing minus IR. Potential difference across a resistor is IR. but I will use a minus sign if I'm going in this direction. I will use a plus sign if because potential decreased, minus sign because potential decreased. If I was going in opposite direction, I would have written plus IR because potential was increasing. I was going from lower to higher potential. So for a current carrying wire, current carrying element, this is how you write plus or minus. Now, for a capacitor, how do you write? Suppose this is plus Q on this plate and minus Q on this plate. And we all know that for a capacitor, if C is the capacitance, then Q is equal to CV. So V will be equal to Q by C. Now, how do I decide if suppose I'm going from point 1 to 2 in this direction? Now, what should I write? Plus Q by C or minus Q by C? I will be writing 1.1 is at a higher potential. It is plus, this is minus. So I will be going from higher to lower. So I will write minus Q by C. If by any chance I was going in this direction in the circuit, then negative plate to positive plate means lower potential to higher potential, increasing potential. So I would have written plus Q by C. So now these three things I have explained to all of you, and we will try to use them in a circuit. Let's see. If suppose I have a circuit in which there is a capacitor, there is a resistance, and there is a battery. Now, I want you to tell me, suppose this is a 20-volt battery and this is the unit of capacitance is farad. This is a 5 farad resistor, 5 microfarad, say. Capacitance is 5 microfarad. 5 farad will be too high a capacitance. And resistance is, say, 2 ohms. Now, suppose at t is equal to 0, I have just connected the battery. Sorry. At t is equal to 0, I just switched it on. The switch is switched on. Now, how do I find what will be the current, what will be the charge on the capacitor? How will this? So this is like charging of a capacitor. Please see this, pay attention. So initially when the battery is connected, there will be some current which will start flowing, and that current will start flowing in this direction. There will be current, and this capacitor will start getting charged. Initially, the charge on the capacitor was 0. Now, this capacitor will start getting charged. So slowly, it will get charged, and finally, it will reach a state where it is fully charged. At that state, suppose the charge is Q naught. So there will be plus Q naught, there will be minus Q naught, and this will be fully charged. When it will be fully charged, there will be no more charge flowing in the circuit. There will be no more, because these plates are not in contact. There is a difference. Once it is fully charged, there will be, so this is stage when the current was flowing and the capacitor was getting charged, that is called a transient state. Transient state. In transient stage, the moment you switch on the battery, current starts flowing and capacitor starts getting charged, and finally it reaches a maximum charge when there will be, after that, there will be no current flowing in it. So a capacitor doesn't allow a current to flow after it is fully charged. Before it is charged, till then, there will be very quickly some current flowing till it gets charged. So let's try to understand this in general terms. If suppose I have a capacitor, I have a resistor, and I have a battery of EMF, say E. This is C, this is R, and this is E naught. Now, I want to find the, and t is equal to 0 pay, I just turn the switch on. Let's assume that the current flowing is I as a function of time, because it will vary. Initially, it will be higher, and slowly it will decrease, and finally it will become 0 when the capacitor is fully charged. So I am assuming I to be a function of time, and This current is flowing in this direction, and there is some charge Q, which is also a function of time. Q is the charge stored on this capacitor. This is plus Q, this is minus Q, and this current enters here. Now, let's apply KVL, Kirchhoff's voltage law. Let's start from this point, A, B, C, D, A. We will be going in the loop A, B, C, D, A. All of you please pay attention. I start moving from A and move towards B. When I'm going from in battery from the negative terminal to the positive terminal of the battery, I am going from lower potential to higher potential. So I will write plus E naught. Increase in potential will be written as plus E naught. For battery, this is the potential difference. Now, I keep going in this circuit. I reach the resistance. There was no resistance. Then I reach the resistance. And now, for resistance, what is the potential difference across the resistance? Please tell me. IR. Potential difference across the resistance is IR. But which sign will I use? Plus IR or minus IR? Let's see. I'm going in this direction. I'm going in this direction. When I'm going in this direction, current flows from higher potential to lower potential. So I'm going in higher to lower, which means potential is decreasing. Potential is decreasing in this direction. So I'll write minus IR. Minus IR. Now, for the capacitor, you are going from positive plate to the negative plate while writing the loop rule, Kirchhoff's voltage law. So when you are going from this direction to this direction, as shown in the figure with this green arrow, you will write the potential difference across the capacitor will be Q by C, and you will write minus Q by C because potential is decreasing. And then you reached here and you reached point A. The total potential rise is equal to 0. And this is the KVL, Kirchhoff's voltage law, that we have applied. And all of you should learn how to apply this. And in parallel, we are now doing some very interesting result. Now let's just solve this equation. Just see this. What happens now? So I is a function of time, Q is a function of time. I can write I as dq by dt. And it becomes a differential equation. And I can easily solve it. If you E naught will be equal to, sorry, E naught, both the terms will go towards the right, R dq by dt minus q by c. This is what we have got. How to solve this differential equation is your mathematics, not physics. So all of you should know how to solve a first order differential equation. I can solve it for you. Find dq. Let's try. R dq by dt is equal to, we have now E naught minus q by c. Okay. Take LCM CE minus q divided by c. Now this becomes dq by CE naught minus q is equal to dt by RC. This is the top. Now, this you can solve. This you can solve and you will get the result. I can solve it. I can substitute C and E are constants. CE naught will be equal to, CE naught will be equal to CE naught minus Q को हम रख देते हैं say some X. So minus dq will be equal to dx. Now it will be solvable. So dq can be written as minus dx divided by x. And when you integrate this, this will be minus ln x. And you can go back to your original thing. Okay, you substituted this as x. So minus ln C E naught minus Q is this. And the limits of Q will be from 0 to Q, and time will be 0 to T. We are going to a general position now. So 0 to Q is equal to dt integral will be what? Where were we? Yeah. 1 by RC T, and time is 0 to T. Okay. Now we'll solve this, put the upper limit, lower limit, and finally you'll get the results, and you get Q is equal to Q naught 1 minus e to the power T by RC. This is what you will get. All of you can see this result in all your books, and this is called charging of a capacitor or a RC circuit. It had a resistance, it had a capacitance, and this is like charging of a capacitor. And here we didn't use too much of physics. All we did is we applied Kirchhoff's voltage law and we solved it. And because the current was a function of time, so we had to do this. And this is called charging of a capacitor. And these results are there in your books. You can see them. If I differentiate this equation, I'll get differential dq by dt will be what? Current. And that will be Q naught. Differentiate. I think it is minus T by RC. Huh? Differentiate it and you'll get the value for current also from this equation. So you will get how the current varies with time, how the charge varies with time when we are trying to charge a capacitor. Now, this is something which you all should know. And now I'll deal with the easier problems, which are, if suppose you have capacitors and the capacitance is say C1. So for a parallel plate capacitor, how do you find the capacitance? Capacitance is epsilon naught A upon D. How many of you can tell me how did I find this capacitance? How does this come? We have two plates. We have one plate here, one plate here. Q charge is given, minus Q is here. You all know that this Q charge and minus Q charge will be distributed on the inner surfaces, and outer surfaces, suppose this is Earth, will have zero charges. Charge distribution should also be clearly understood, known. Just now, because I realized that the lecture was becoming boring, so I restrained myself from going too deep into the finding the distribution of charges, but one should have that clarity. But abhi yahan pe chalta hai. So how do we find that this is the capacitance? Please see, you gave Q charge to this plate. You find the electric field here. How do you find electric field between the plates? Q by area. This is sigma upon 2 epsilon naught. This is electric field due to this, in this direction. What will be the electric field due to this? It will be in the same direction. One is repelling, one is attracting. One is repelling, one is attracting. Now, so both will get added. So Q by 2 epsilon naught A. This is the net electric field due to these two layers of charge. And net electric field is uniform. You can see it is not varying between the plates. And if I find E dot dl from here to here, E dot dl, that will be E into this length, D distance between the plates. E into D will give me the potential difference, which will be V. V plate, V of this plate, and V of this plate is 0 because it is earthed. So V of the potential difference between the plates will be this. Now, we know Q divided by V will give us the capacitance. So capacitance will be Q by V. And when you solve this equation, you will get C is equal to epsilon naught A upon D. And you can see capacitance doesn't depend on the charge or the voltage. It depends on the geometry of the plates, area of the plates, distance between the plates, and this is the capacitance of a parallel plate capacitor. Now we will do, I'm just doing the theory, the concepts involved, and now let's do some questions. Suppose I give you a question. Uh, there are two capacitors connected like this, and you don't have to know any result, cram, series, parallel, whatever. I just want you people to, and now this is a battery, and I want you to find what is the total charge on each. There is another, find the total charge. You don't need to know any results for about series parallel. Now, this is 10 volt, this is 20 volt. If we will use Kirchhoff's voltage law, which is like a basic rule, which all we should know. This is say 2 microfarad, 5 microfarad. This is 10 microfarad. These are three capacitors, and I want to find, will there be any current flowing in these when the capacitors are charged? No. So please understand, only in the transient stage, when switched, the capacitors were uncharged and we turned on the switch, in that case, they start getting charged. But once a steady state has been achieved, once the capacitors are charged, then there is no flow of current. And now the question is, find the charge on each capacitor. These are the two batteries. The steady state has been achieved. You have to find the net charge on each capacitor. All we will do is we will apply Kirchhoff's voltage law. Just see this, how to do these questions. Assume that Q charge flew from this battery here. So there will be plus Q on this, minus Q on this. All of you should understand this much. If there is minus Q here, there will be plus Q on this. Why? Conservation of charge. So there was net charge 0 here. Please see this. Net charge on these two is 0. So if this was plus Q, this will be minus Q on this plate. Now, if this is plus Q, this will be minus Q. For a capacitor, you know that if one plate has charge Q, other will have minus Q. Now, again, the same thing. Here, I Q plus Q minus Q. And now for this point, there will be some plus Q charge flowing from here. So let's assume this is Q2. So this will be Q minus Q2 going this way. Q2 charge goes like this. This is Q2. This is minus Q2. And Q2 comes here. Q1 minus Q2 comes here. Q charge comes here. And the charge conservation has been applied. Now let's write down the equations for, in fact, if you see, the moment I have connected these 2 points, I have short circuited it. There is no potential difference remaining between these two. So in a way, I have short circuited. So this can be avoided. We can do away with this. I can add a battery or something. Otherwise, it becomes too easy. यहाँ पे short circuit कर दिया है, तो भाई यहाँ पे तो कोई चार्ज ही नहीं जाएगा, ये बैटरी से कोई कुछ, ये तो बिल्कुल सेम पोटेंशियल पे हो जाएंगे. सो दिस क्वेश्चन विल बिकम लाइक कि ये इतना ही क्वेश्चन रह गया. आप ये रहा, ये क्वेश्चन रह गया. इधर वाली कहानी को तो आपने चेंज ही कर दिया. So let me just give you some standard questions which I have kept for you. Let's try to do those questions. Let's see. ये क्वेश्चन करते हैं. एक मिनट रुकिए, मैंने इनको अलग भी स्टोर किया. So I have kept some questions for you people which you should attempt, and I want to give you a question. Let's do this question. This has come in an entrance exam of yours. Just try to do this. It's a small question. I want everyone to try. This will clear your concepts. First, we'll try this, then we'll go to the circuits, and then you will develop the confidence. So we will try to do easy questions first so that the whole theory and the concept that we have been discussing comes into full clarity for you. So just keep paying attention and tell me. Try to do this question. I will solve it for you after that. मरुदेश सॉरी 11th क्लास अभी ये 12th वाले बच्चों के लिए ये टॉपिक हम कर रहे हैं दे हैव देयर कॉम्पिटिटिव एग्जाम्स very soon, so this was requested by people and that's why we are taking this class. 11 children will be patient. Okay, now let me do this question. Has anyone done this question? Okay, I have received replies. Let me do this. A parallel plate capacitor is charged by connecting a 2 voltage battery across it. It is then disconnected from the battery. So there is a parallel plate capacitor. It is connected by a battery. Will I be able to charge it like this, or there will be some resistance needed? Yes, there will be some resistance needed. There will be some resistance in the wires, even if I try to charge it without any resistance. Now, but when it has been charged, so there will be no current in that. Now, 2 voltage battery, it's 2 volt, and a parallel plate capacitor is charged by 2 volt battery across it. It is then disconnected from the battery and a glass slab is introduced between the plates. Which of the following pair of quantities decrease? So when there is a parallel plate capacitor, the capacitance of the parallel plate capacitor is C is epsilon naught A upon D. It doesn't depend on Q and V. If you bring a dielectric slab inside a capacitor, the only thing that happens is if you fill the whole material with K dielectric constant, then the capacitance will become K epsilon naught A upon D. So instead of epsilon, it becomes K epsilon. K is the dielectric constant. Now, and its value is greater than 1. So if you have filled it with a dielectric slab is introduced between the plates. Just see what is written here. See this. Dielectric slab is introduced between the plates. So a glass slab is introduced between the plates. Which of the following quantities decrease? So capacitance increases, energy stored and capacitance. Obviously, capacitance will increase, and let's see. What is energy stored in a capacitor? Energy stored in a capacitor is energy of a capacitor is Q square by 2C or half CV square. If you substitute Q is equal to CV, you will get this. Am I right? Or another way of writing it is half QV. So they are both, all three of them are same things. Now, if you are keeping if a dielectric slab is introduced, so when we introduce a dielectric and the battery has been disconnected, please see this, disconnected from the battery. These are important terms. When it is disconnected from the battery, the charge will not be able to flow anywhere. So the charge will remain the same. If there was any charge, whether you introduce dielectric or not, Q remains the same because battery has been disconnected now. Now, Q remains the same. If capacitance increases, so the energy will decrease. You can see Q remains the same if I use this formula. So we cannot say energy stored and capacitance both increase. No. Charge and potential difference. Charge doesn't change at all because battery has been disconnected. This is also wrong. Capacitance and charge. Q is equal to CV. C has increased because of the dielectric K. Therefore, Q also increased. So C is the correct answer. C is the correct answer, and all other are wrong. Now, let's take another question. Just try to do this question, all of you. Please try to do this. This is a typical case which I want all of you to understand. Please read the question, then I'll solve it for you. We are doing some basic questions to get you the grasp, to get you the feel of this topic, chapter, and you are able to solve questions. तो थोड़ा सा alert रह के try to solve these questions. I'm reading your chat on this thing, YouTube. Children, please focus on studies and not waste time on passing comments. There is no point. If you have to do this commenting thing, you should do it somewhere else. It's just a lecture of physics where someone is trying to teach you physics and you should try to learn it. Wastage of your time is all I can say if you are just writing comments and not paying attention to studies. And so focus on your studies. 5 capacitors, each of value 1 picofarad, each of value 1 microfarad, are connected as shown in the figure. The equivalent capacitance between A and B is. How do I find the equivalent capacitance between A and B, and why I have chosen this question? Please see this. If I draw this diagram, this is like a typical question which I want everyone to be clear about. A and B are these 2 points, and I draw this capacitor which is like 1 microfarad, and then it is connected at a point, say X and Y. This is X. Now, there is another, from X, there is another capacitor which is connected to B. There is another capacitor from A connected to Y. And Y and B have 1 capacitor. And there is a capacitor between X and Y. Now, this is a Wheatstone's bridge. And these kind of questions are asked. They come in competitive exams, and you have to have the ability to identify this kind of situation. And whenever Wheatstone bridge is there, what they play is, it's, if you try to solve it, lengthy solution, you can use Kirchhoff's voltage law, calculations will be lengthy, but finally you arrive at a result which can be immediately told. Just see this. If this is 1, this is 1, this is 1, this is 1 microfarad. If C1 is this, suppose C2 is this, C3 is this, C4 is this. In general, if C1 by C2 is equal to C3 by C4, this is called a balanced Wheatstone bridge. And if balanced Wheatstone bridge is there, you can just simply remove this capacitor and there'll be no role of this capacitor. So you just do away with this, and these 2 capacitors will become parallel. These 2 will be, series, and this capacitor will have no role. You can just eliminate that. This is called a balanced condition of a Wheatstone bridge. All you had to do is you had to identify this, and the moment you do that, now 1 and 1 are in series, this 1 and this 1 are in series, and they both are in parallel. So equivalent capacitance when they are in series is 1 by 1 plus 1 by 1. In case of capacitors, the result of equivalent capacitance is for series combination R equivalent, for series R equivalent used to be in resistors R1 plus R2 plus R3. यहाँ पे for parallel combination, you will have C equivalent will be equal to C1 plus C2 plus C3 and all. For series, it will be 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2, and this will be the result. So this is opposite to resistance. So remember these results, and you can directly apply, and you can see C equivalent for these 2 will be for these 2 this and this will be there in. This has been omitted because it's a balanced Wheatstone bridge. So they are in series. So 1 upon C equivalent is equal to 1 upon 1 plus 1 upon 1, and there'll be 2. So C equivalent is 1 by 2 for upper 2. For these two, again the same story, 1 by 2. C equivalent 1, C equivalent 2 is 1 by 2. And if I want to find the total capacitance between A and B, and that is say C equivalent, that will be, these two are in parallel. So 1 by 2 plus 1 by 2, that is 1. So the answer is 1, and this will be the answer. B will be the answer. Now, let's do few more questions. Try to do this. I want you to understand what is E dot dl. Try to do this question. These are basic questions, and I want you people to understand that when you get the flair of doing questions based on the concepts, then you develop confidence. So let's do these easy questions and try to, and they have been a part of your competitive exams in past. A uniform electric field E exists along horizontal direction as shown in the figure. The electric field at A is VA. The electric field here is VA. This is VA. A small point charge Q is slowly taken from A to B along the curved path as shown. The potential energy of the charge when it is at point B is. So it is taken like this on this path and it reaches B. Now, can anyone tell me electric field is a conservative force field or non-conservative? It is conservative. Therefore, E dot dl will be, VA minus VB will be independent of the path chosen. And if it is independent of the path chosen, I can find the electric field E dot dl for this path, and I'll still get the same answer. And now you know E, uniform electric field E. E is uniform, it is not changing. So E into X will be E dot dl from here to here, E into X, because I found for this path and it remains same for every path because it's a conservative force field. So E into X is the potential difference. So VA minus VB is equal to EX. So potential of B, he has asked us what? A point charge Q is taken from A to B. The potential energy of the charge when it is at point B is what? Okay. So QVA is the potential energy at A, QVB is the potential energy at B, is equal to QEX. Now, we have to find potential energy at B. So it will be QVA minus QEX. Potential energy of the charge when it is at point B. Okay, let me just tell you. So work done, potential energy at A is Q into VA. This plus work done by electric field will be Q into E, that will be the force, and force into X will be the work done. This work done plus potential energy at A should be equal to potential energy at B. That should be QVB. Now, what he's asking is potential energy of the charge when he is at point B. So we have to find this. So this should be QVA plus EX. Yeah, this is the answer. B is the answer. Good. Now, okay. Now let's do some more practice problems, and I will make you understand few more things which should help you in this chapter. If you have any questions, you can write in the chat and I'll ask you, answer your questions. Now, let's do some series parallel or some questions of Kirchhoff's voltage rules applied. Now, just see this. Let's do this question. There is a capacitor plate There are two capacitors. This is one capacitor. This is a battery. Let's practice a few problems. There is another capacitor. Battery is 10 volts. Another capacitor. Another battery. Now, this is 20 volts. And this is, say, C1 is 10 microfarad, 5 microfarad. And this is, say, 2 microfarad. Now, please tell me what will be, I want you to learn how to use, जैसे आप एम्पियर ये किरचॉफ्स रूल लगाते हैं, वो वाला रूल लगाने की यहाँ पे मैं आपको प्रैक्टिस कराना चाहता हूँ. दैट इज माय एम, जिससे कि आपको कभी भी इसमें अटकने ना हो. ये लीजिए, दिस इज द क्वेश्चन. ये है 4 माइक्रोफैरेड. नाउ फाइंड व्हाट विल बी द चार्ज ऑन दिस. इस पे चार्ज कितना होगा? Tell me what will be Q on this capacitor. Bus, that's my question. In steady state, so I have ensured, I have told you that the capacitors have got charged. Transient stage is over. When steady state has been achieved, at that time, all the capacitors are charged. Find what will be the charge on the 5 microfarad capacitor. Please try to do this. I want you to practice some things, how to write the Kirchhoff's voltage law in this case of capacitors. Give it a try. I want all of you to try. Kirchhoff's laws haven't been taught. Okay. 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 This is little Kirchhoff's rules for current. Okay. ठीक है. So then in that case, I can teach you that from the basic. If you have not been told, there are only two rules. Just pay attention, everyone. Please pay. There is a thing called conservation of charge. So you will be doing, okay, capacitance you are doing right now, current. So there will be a chapter next to this where you will be doing current. And there also you'll be using this Kirchhoff's rules. So there is one thing. If you have many resistances connected at a point, just pay attention. I'll teach you right now so that it helps you. R1, R2, R3, and this is a junction. This is also called junction rule. I am telling you Kirchhoff's rules right now. If some of you who do not know, this is called junction rule. So if there is I1 current here, I2 current coming here, then the current in this has to be, suppose I3 is coming here, all three are coming here at this point. Then I1 plus I2 plus I3 should be equal to 0. What does this mean? This means conservation of charge. This is a very interesting, important thing I'm teaching you. Conservation of charge. What does this mean? What is I1? I1 is the rate of charge flowing per second towards this point. I2 is the rate of charge flowing per second towards this point, towards this junction. And I3 is the rate of flow of positive charge towards this junction. And at this junction, per second, this much charge is arriving. And we know that at any point, charge can neither be created nor destroyed, right? So what should be done? Like, so this gives me, कि भाई, if I1 is positive, I2 is positive, then I3 has to be negative. So junction rule says, because there was no net यहाँ पे, there was no charge here at this point. It is not like a sink of charge or a fountain of charge. So charge cannot disappear here. If this much charge arrived here, this much charge arrived here, this much current. Current is what? Charge only. So this much per second, this much charge is coming here. So that charge cannot get destroyed. It cannot disappear. Therefore, we say that I3 will be, or I1 will be equal to, I3 will be equal to minus of I1 plus I2. What does that mean? Okay, if this is say 10 ampere, this is 20 ampere, then the same amount of charge should leave from here. And therefore, this should be minus of these two. So this is 30 ampere. Now, so Kirchhoff's junction rule says that net current coming to a junction should be equal to net current leaving from the junction. So if I now want to write the Kirchhoff's junction rule quickly, if there is a junction of many wires, and this is based on conservation of charge, and it has I1, I2, I3, and this is I4 and I5. So you can see these two currents are leaving and these two currents are entering the junction. Now, what should be the relationship between all five of them? I1 plus I2 plus I3 is equal to I4 plus I5. And where are we getting this equation from? What is the core of this junction rule? Conservation of charge. Charge can neither be created nor destroyed at any junction. So, jitna charge, any amount of charge that was entering here should be equal to the same amount of charge leaving from here per second. Therefore, the currents should be related like this. This is called junction rule. Now, the junction rule for the conservation of charge for plates, for capacitors, should also be understood properly. Please pay attention here. If suppose I tell you that there is a capacitor here, there is another capacitor here, there is another capacitor here, and then I have battery. Now try to understand this. This is say 10 volt battery. Now, if suppose all four of them are in series, just see this. And series hota kya hai, use samajhiye. You need to understand and get clarity what is happening. Suppose this battery sent some current, some charge, positive charge here, and finally steady state has been achieved. After some time, there is no flow of current. So capacitors don't allow flow of current. There can be a very small current for a very small duration only when, for how much time will it be there? Till the capacitors get charged. And that happens slowly. The transient stage is, that is called the transient stage of charging of a capacitor. Similarly, you have discharging of a capacitor. But those transient stages we are not dealing with right now. We are saying in this circuit, we have charged the capacitors and we want to find what are those charges and we want to apply the conservation of charge rule. So if there is plus Q charge on this, there will be minus Q naught charge here. If there is minus Q naught here, now you see this. This is an isolated system. They are not connected to anyone else. So if this plate, the charge is plus minus Q naught, on this plate, it will be plus Q naught. And this is based on what? Law of conservation of charge. And that's why when you have capacitors connected in series, so this will be plus Q naught, this plate will have minus Q naught. And why is this plus Q naught and minus Q naught business is happening? I explained that to you in using Gauss theorem, that for a parallel plate capacitor, how we find the electric field in between and how we arrived at that result that inner plate will have plus Q naught and minus Q naught charge. I showed you that. Now coming to, in this case also, this will be minus Q naught. Now you can see this system is also isolated. This, and you can apply charge conservation here. If this is minus Q naught, it should be plus Q naught. If this is minus Q naught here, it will be plus Q naught here. Gauss theorem. Again, this This is isolated. These two plates, you can see they are not connected with anyone. They are just kept close. But this in is in isolation. And if it is in isolation, charge has to be conserved. And this is plus Q naught. So it should be minus Q naught plus Q naught. And finally, you'll see this is the charge distribution. And you understand the logic why, in case of series, why the capacitors have the same charge. And this whole thing is based on what? This whole thing is based on law of conservation of charge. Now, if we have these charges and I want to apply KVL, Kirchhoff's voltage law, so that second rule I have to teach you. Now, coming back to Kirchhoff's rules. So Kirchhoff's voltage rule will help you in KVL, will help you in capacitors also, in electric current also, and you all need to understand this. Pay attention. Suppose I have a resistance R1. I have a battery here, 10-volt battery. I have another resistance R2. I have another battery, 20 volts. And there is a third resistance. Forget about this series parallel thing. Just how do we find the current in this circuit? If we can assume any direction, current to be starting in any direction, if suppose the current was actually not in the same direction, it will come out to be negative. So you don't have to worry about this is a 10-volt battery, this is positive and negative. This is a 20-volt battery, this is positive and negative. And this battery will push charge more, this battery will push charge less. You don't have to get into that confusion. Now, just assume some current I1 started from this battery, from this point. And this I1 current is flowing through this resistor. Now, on this, there is, ये तो junction ही नहीं है, ये तो सिर्फ turn है. So I1 current is coming, I1 current is coming, I1 current is coming, flew through this resistance. This is R3, suppose. And they reached this battery. I1 current entered this battery. So the same amount of current should leave this battery, I1. And I1. And the same amount of current entered. Now, please remember one thing. Law of conservation of charge says charge can neither be created charge can neither be created nor destroyed. Therefore, we will, any amount of current that leaves a battery should enter the battery. You can see that happened here also. Now, तो यहाँ पे junction rule से ज्यादा मेरा focus है in telling you the Kirchhoff's second rule, loop rule. This is also called loop rule. Now try to understand what we are going to do. Let's name A. Let's name these points. A. There is a loop. A, B, C. We started from A, went to B, C, D, A, back to A. What is the potential difference between A and A? It's zero. So the total potential increase or the total potential decrease will be zero because we reached the same point A after completing the loop. Now, let's write. Now, I am going to, the convention that we use is potential rise, we are taking positive. So tell me, When I started going from A and I am traveling like this, I went from the negative terminal of the battery to the positive terminal of the battery. And the potential difference between these two terminals is 20 volt. That is given to me. Now, can anyone tell me, should I write plus 20 or minus 20 when I am going in this direction through the battery? Plus 20. Because potential increased, we went from minus to plus. Please pay attention here. If you don't know the loop rule, Kirchhoff's voltage law, this is what I'm teaching you here. So I will write plus 20. Now, I am now going in this direction. I encountered, there was no resistance, nothing. I encountered a resistance here. The potential difference across our resistance is IR. So I1 into R2. That is the potential difference. But I have to put a sign. Sign has to be plus or minus. So did the potential decrease from across this or potential increased? So you can see when I was going in this direction, I'm moving like this in the loop. This current flows from higher potential to lower potential. Therefore, if I have assumed the direction of current to be I1 and the current is flowing in this direction, I1 current is flowing. So I am going from higher potential to lower potential. That means I will apply a minus sign, potential decreased. Next we encountered a battery. Now battery again has a potential difference 10 volts. Now I have to choose which sign to apply. We are going from negative terminal of the battery to the positive terminal of the battery. Therefore, I should use potential increased. I should use plus 10. Now, I'm moving again. There is potential difference across this, which is how much? I1, R1, IR. Potential difference, Ohm's law. Across a resistor is V is equal to IR. So, I will use I am again moving in the direction of current. Current is also going in this direction. If I'm moving in this direction, next question I'll show you where we'll be moving against the current. Then what we write. So this, please try to understand. Next one, you will be thoroughly clear. Now, we are moving in the direction of current. Current is also flowing in this direction. Current has to flow from a higher potential to a lower potential. Therefore, the potential is decreasing. I write minus sign here. Now there is no resistance and I'm moving. I come across this. This is potential difference will be I3, R3, I3, R3. Sorry, I1, R3. And what sign should I put? We are moving in the loop in this direction. The current is also flowing in this direction. Current flows from higher potential to lower potential. Therefore, this will be minus, decrease. And now I reached back the same point. A total increase in the potential was positive. Total increase is 0. So increase, decrease, decrease, increase, decrease, and decrease, and finally total increase is 0. This is Kirchhoff's voltage law. I will illustrate one more problem and I'll show you how we will use the rule. Please pay attention. And then I'll come to capacitance. So one is there is a battery, there is a resistance, there is another battery. I'll give another battery in this direction now. You don't have to cram any formulae. All you have to do is learn these two rules and you will be able to solve circuit problems. Most people will try to tell you, find equivalent capacitance. Arey bhai, that is a small component of the whole chapter. Equivalent capacitance and equivalent this thing. Resistance is not what you should be focusing on. Focus on the basics, and the basics are Kirchhoff's voltage law and conservation of charge. Loop rule. So let's see. We'll do another. So you are doing right now your current chapter also, and you are also learning The same thing in capacitance also, and I will be doing both now. Now I have got 1 ohm, 2 ohm, 3 ohm, 4 ohm. These are resistances. This is a battery which is 10 volt, 20 volt, and 30 volt battery. And I want to find what will be the current in this, or I want to find the currents. So let's understand. Suppose you don't have to worry about how much current is flowing from which battery, and you have to know that beforehand, or there will be a mistake. No, there will be no mistake. You assume I1 current started from this battery. Just assume this. I1 current started from this battery. I1. Now, I1, this is a junction. Here you have 3 wires. So some part of this will go into this battery and some part will go straight. So I assume this is going, say, I2. So this current will be I1 minus I2. Can anyone tell me where did I get this? Why I2 and I1 minus I2? Junction rule, law of conservation of charge. If I1 current is entering this junction and I2 is leaving this side, the remaining current should go this side. And we have applied junction rule. Now, so this is I1 minus I2, it goes like this. It is coming like this. Charge cannot disappear anywhere. Now, if I2 entered this battery, I2 should leave this battery. I2 will be moving like this. And this is I1 minus I2 everywhere in this wire. And this current and this current, again, they meet at this point. This is the current entering, this is the current entering this junction. So the leaving should be, this current should be this plus this. And if you add these two, you will get I1. And I1 is moving now here. This battery will have I1 entering, leaving is I1. And you can see I1 current finally entered this battery. So there was no loss of charge. Therefore, we are sorted with the junction rule for sure. The proof that the amount of current that left a battery, the same amount of current entered that battery while you were writing equations will prove to you that you have not made any mistake in the conservation of charge. That is the proof. So we have done the first part successfully, and now we will now do the second part, and the second part is the loop rules. I have how many unknowns here? Everything else is given. I have I1 and I2. I have two unknowns. If I know I1 and I2, I can tell you the current in any resistance. So there are two unknowns that I have. So I need two equations, and those two equations will come from two loops. Let me name the loops. I am naming the loops as this is A, B, C, D, E, F. Now just see, I will write the equation for the loop A, B, C, D, A. That is one loop. Then I'll write the equation for the loop A, D, E, F, A. I should begin at the same point, end at the same point. Then you have completed the loop. And that's why this rule is called loop rule. So let me first write down the equation for this loop because we can see that on the screen. Now, we are starting from A, moving towards D. So this is our journey. Now, current is moving. We are moving in the direction which is opposite to the current. Current is moving towards right. We are in the loop. When we are going in this loop, we are moving like this. Our direction of motion is this. So am I moving opposite to the direction of current? Yes. Now, pay attention. Current is always going to move from higher potential to lower potential. So the potential of this and potential of this has to be higher, this has to be lower, because current is moving in this direction. I2 is moving in this direction as shown in the figure. Now, I will write the potential difference across this resistance, 3 ohm resistance, will be IR, I2 into 3. But I have to apply a sign. What should be the sign? Plus or minus. I am moving in this direction, this direction. I am going like this. So I am moving from a lower potential to a higher potential while writing this equation. This is how I'm going. So plus lower to higher is increase. There is an increase in potential when I'm going from L to H. Now, that's why I put not minus IR, but I put plus IR because I am moving in opposite direction to the current. Now, battery. We reached here. Battery is 30 volts, so 30. And I'm going from negative terminal of the battery to the positive terminal. So there is an increase in potential. Go to D, go to E, there is no resistance. Now, here, we reached here. The potential difference will be 4 I1 minus I2. I have to apply some sign. I am going in the direction of current now. And current has to flow from a higher potential to lower potential. Current is flowing in this direction. I shown it by the arrow. So when we are moving in this direction, we are going from higher potential to lower potential. So it will be decrease minus sign. And then I reached this point A. There was no resistance here. So the total increase should be equal to 0. And this is the equation for loop rule, Kirchhoff's voltage law. And I am trying to slowly teach you the correct way of writing the Kirchhoff's voltage law equations. Now we will be using the same equations in capacitors also. There, the only difference is for a capacitor, potential difference is Q by C. That's it. Again, there also we'll see whether the potential is increasing or decreasing, and accordingly we'll write the equation. So please learn these two rules: junction rule, charge conservation, voltage rule. Now, let's write down this equation also. A, B, C, D, A. All of you can write it down, I'm sure. I will quickly tell you here itself. I think there is too much of space occupied. I can rub this so that we keep seeing the thing and keep writing the thing. Okay. Let's come to this loop. The loop's name is A, B, C, D, A. I'm going to write the equations for A, B, C, D, A. I hope all of you are paying attention. Just understand, I started moving from A. I'm going in the direction of current. I am moving from A to B. This is how I'm going. And the current is also flowing in the same direction. You can see I1. So I'm moving in the direction of current. Current flows from higher potential to lower potential. So for current, 2 ohm resistance, I1 IR, I1 into 2. But what sign should we put? Our path is from higher to lower potential, so minus IR. Then we reach the battery. Battery may, now we are moving from positive terminal to the negative terminal, which is the potential difference across the battery will be 20. But my path is this now. I am going in this direction. So I am going from positive plate to negative plate. So minus 20. Here, now you can be fast. 1 into I1, I1 into 1 ohm, and minus, because potential is we are moving in higher to lower. Current flows from higher potential to lower. Now, for this battery, plus 10. Now I can be fast. I reach D. Now, for this, was there a battery? Yeah, there was a battery here. There was a battery here, which got rubbed. Okay. Now, I am going in this direction. So, minus 30. And then this time we are moving in this loop. Please try to see this. Oops. We are moving in this loop. A, B, C, D, A. This is our path. Now, for the battery, minus 30. For the battery, I'm going to write here. Minus 30. And for this current, for this, how much ohm was this? 1, 2. This was how many ohms? Did I give you this? Okay. Suppose this is, say, 4 ohms. This resistance. I think I had given the value. Got it. Rubbed. I think it was 3 ohm or whatever. Jubi. No. I think 3 ohm. 1, 2, 3 liya hoga. Huh. Now, but I'm moving in this direction. So it'll be I2, 3 I2, IR, but I'm moving in direction which is opposite to the direction. No, in the same direction as direction of current. The current is in this direction. This is the direction of current. And therefore it will be minus 3 I2. And I reached A. And the total increase in potential should be 0. This is the other equation. Now, if you have learned how to write these two equations, you are sorted. Then you will be able to, because we are using too many colors. We first wrote the equation for this. We then wrote the equation for this. So there is a little hodgepodge that you are seeing right now. But I hope you are getting what I am trying to explain to you. Now let's use the Kirchhoff's rules for a circuit using capacitors also. So I want you people to understand this. This will help you in your current chapter. This will help you in capacitance, and this is LCR circuits also, where you'll have inductor also. Everywhere, see, there are 4 elements. Sine ka, Aryan, I've just explained how to write the signs, and I've done it in detailed, slowly. I hope you are clear now. Anyways, just pay attention. There are 4 elements. Just remember this. You will face in your full electricity and magnetism. One is your resistance, R. Other is capacitance, C. This is the symbol. One is your battery, EMF, voltage, E naught, whatever. And fourth will be your inductor. Inductance will be L. Now, for all these 4 elements, if you just learn how to write the equation, and so for resistance, if I current is flowing, then the potential difference across this will be IR. If for capacitance charge is Q, the potential difference across the capacitor will be Q by C. For battery, the potential difference is E naught only. For inductor, the potential difference will be L di by dt. That will be the potential. Wahan pe changing current is changing. If current will change, then there'll be inductance will play an important role, and there'll be a magnetic field. Changing electric field produces magnetic field. Changing magnetic field produces electric field. We'll come to this later when you will be doing inductors, when you'll have studied magnetism, and you will learn EMI, electromagnetic induction. Then you will be using this term. But these are the only 4 terms that you'll be using in circuits, any circuit. Now, for all these 4, you should know that how you have to write the equation and how you have to determine the sign. Just please pay attention. This one is, say, after magnetism, you will learn, but these 3 right now, every one of you should be clear. Suppose current always flows in any wire. If you have assumed this to be the direction, current always flows from higher potential to lower potential. So now, while writing the equation, if in a circuit, in a loop, you are moving in the same direction as that of the current, अगर आप ऐसे जा रहे हैं इक्वेशन लिखते हुए, तो आप लिखेंगे you are going from higher potential to lower potential. That means potential is decreasing. So if I am assuming potential increase to be positive, then potential decrease has to be negative. So I will write minus IR. If suppose I was going in opposite direction while writing the equation, not in this direction. Suppose I was going in this direction while writing the equation, not this direction. The current is still flowing in the same direction. My direction now is different. My direction now is different. My direction now is this. While going in the loop, while writing the equation. In that case, I will be writing, I am going from lower potential to higher potential. For the same IR, I'll write plus IR. So you should know in which case you will write plus IR, in which case you will write minus IR. This clarity every child should have. Then only you will be able to write the equations, solve the questions, whether it is current, electric current, whether it is capacitance circuits, any circuit. Same way for this, if you are going in this direction while writing the equation, you are going from a positive plate to a negative plate. So you are going from higher potential to a lower potential. So you will write this is decreasing. If you are going from higher to lower, in this direction, you are going from higher potential to lower potential, positive plate to negative plate. That means your potential is decreasing. So you will write minus Q by C. If suppose for the same capacitor, I was going while writing the equation, I was going in this direction, what will I write? Plus Q by C. The same potential difference. Now I was going from a lower potential to a higher potential point. The potential increased. So Q plus Q by C. So, and for battery, if you are going in this direction, you are going from a lower potential to a higher potential. This is called positive terminal. This is called negative terminal. So negative to positive you are going. So if you are moving in this direction, you will write plus C naught. If you were going in opposite direction like this for the battery, you were supposed to be going from positive plate to negative plate, you would have written minus E naught. Now, these are the three things which every child should know. And once you know these three, for any circuit, you will be able to write the correct equations. Now, let's practice some questions for capacitance, where so there is one series and parallel derivation. Quickly, I'll do it because they also are derived from this only. See, I'll show you. Suppose I have a capacitor C1, I have a capacitor C2, I have a capacitor C3, I have a capacitor C4, and so on, Cn. And I have connected them to a battery. No, I want to find the result that you use for finding the equivalent capacitance is arriving from here only. Just see, if E naught is the battery, suppose I want to find the charge. Suppose this has steady state has been achieved. There is no transient stage. There is no current flowing. Capacitors don't allow, when they have reached a steady state, they don't allow current to flow through them. So if steady state kabhi bhi mention hoga, to you will take current flowing through the capacitor will always be zero. Only in transient stage for some time till it is getting charged, till then it allows to current to flow. Steady state means zero current through capacitor. तो किसी भी सर्किट में अगर कैपेसिटर दिखाया जाए और बोल दिया जाए स्टेडी स्टेट हैज बीन अचीव्ड, तो जो कैपेसिटर जहां कनेक्टेड है उस आर्म में करंट विल बी जीरो, चाहे उसमें रेजिस्टेंस बैटरी कुछ भी लगाते रहो, current will be zero right now. So current in this circuit will be zero. Steady state has been achieved. Now, suppose the charge on this is Q1 plus, it will be minus Q1, it will be plus Q1, minus Q1. And I have explained why. If it is minus Q1 here, we know these two plates are isolated. ये isolated है. ये देखिए कौन सी वाली, ये तो इस पे अगर माइनस Q1 आया तो इस पे प्लस Q1 आ जाएगा, और ये सब मैं पहले एक्सप्लेन कर चुका हूँ. नाउ minus Q1 plus Q1 and the charges are same on every plate, minus Q plus Q minus Q, and each capacitor has the same charge. And I have also explained that the net charge nahi baat karta hai, which when we say charge on a capacitor, we mean one plate, charge on one plate, the modulus of that. So charge on each capacitor is like this. Now I want to write the amperes, this thing, KVL, Kirchhoff's voltage law in this loop. Let's start from A, B, C, D, A. We'll reach back A. Now, this is how we are going while writing this. And we are reaching the same point. Now, let's write down. A say we start from A. We reach the capacitor. The potential difference across the capacitor will be Q1 by C1. And I'm going from in this direction. So I'm going from positive plate to negative plate. So decreasing minus Q1 by C. Similarly, minus Q1 by C2, minus Q1 by C3, minus Q1, Q1 by Cn. And then I reach the battery, and battery ke liye I'll write plus E naught is equal to 0. From here, I get E naught is equal to Q is common, 1 by C1 plus 1 by, 1 by C1 plus 1 by C2. Q1 is common, and so on, 1 by Cn. Now you can see E naught is V only. Now, what is equivalent capacitance? Suppose I remove all these capacitors and I remove and replace them by one single capacitor. Then that capacitor will be equivalent to all these capacitors. So suppose that capacitance is C equivalent. What will I write? Q is equal to CV. So Q1 is equal to C equivalent into E. So from here, I'll get 1 upon C equivalent will be equal to E naught by Q1. Now equate these two. E naught by Q1 can also be found from here. Q1 को हम इधर ले आए. Now, so you will see this is equal to 1 upon C equivalent. So now when capacitors are in series, this is how you find the equivalent capacitance. And how we arrived at it? We used Kirchhoff's voltage law and we arrived at this. Let's try to do some questions. I think we should continue the class again. And in the next class, what we'll do is we will do numericals based on the theory that we have learned today. And with this theory, if you go home and try to do questions and use these rules and the concepts that we have learned, you will be able to solve a lot of questions for sure. I'm sure this clarity will give you some advantage in understanding and solving the questions and problems. In the next class, we'll try to take you to the higher level where we'll do current also, magnetism also, and solve miscellaneous problems. So in bits and pieces, slowly, you'll develop that confidence and clarity. Right now, because you have not done current and Kirchhoff's rules, so maybe you may find things a little uneasy if you have not done things ahead or if you have not done things behind, because most of the things are interconnected. So you need results and formulae of previous things also. You need results and formulae for next things also. So, but certainly with this lecture, I'm sure that there is some more conceptual clarity that you added to your knowledge. And I will try, if needed, to take more lectures and ensure that you people develop that confidence and clarity. Thank you so much, everyone. Thanks a lot. Thank you.